Module 3, Lecture A, Workflow and Baselines. By the end of this lecture, you will be able to describe the steps in an end-to-end machine learning workflow for civil engineering data, implement a manual train test split using simple Python and NumPy operations, and build baseline predictors for regression and classification before training complex models. ML pipeline, problem framing. When framing a problem, clearly define the inputs, outputs, scope, and constraints. This includes what data the model will use, what it should predict, the time horizon, and the operational setting. Practical limits such as data availability and regulations shape how the model is prepared, chosen, and deployed. These choices help ensure the model fits real-world needs and supports either human decisions or automation. In civil engineering, problem framing should define what makes a model useful in practice, not just accurate. Engineers must consider which errors matter most, connect performance to outcomes such as safety or cost, and compare results against a clear baseline like current practice or historical data. This turns machine learning into a structured way to support practical, defensible decisions. Python code, problem framing. Before building a model, first frame the engineering need clearly. Define the inputs, outputs, and what success should look like. Then compare the possible tasks before choosing a method. We begin by importing pandas and NumPy, which prepare the environment for data analysis. Pandas helps work with structured table data, while NumPy supports numerical operations on arrays and matrices. A pandas data frame is used to organize small civil engineering project examples for analysis. Each project records the engineering need, the relevant inputs, the prediction target, the task type, and a baseline for comparison. This structure turns practical problems, such as traffic prediction, into clear regression or classification tasks, ready for modeling. Check that the project's data has 3 rows and 5 columns, confirming the expected structure. Then, make sure the output column has no missing values, so the target data is complete and ready for modeling or further analysis. To measure how complete each project's problem framing is, we check whether key fields are filled in: the need, input, output, type, and baseline. The framing score is the count of these fields that are not missing for each project, giving a simple completeness measure. A specific framed problem is selected from the project's data, then reviewed as an example of turning an engineering need into a prediction task. The narration identifies the need, the available inputs, the target output, the task type, and the baseline used for comparison. It then reports a framing score, which summarizes how many required problem framing elements are present. The script creates a structured framework for civil engineering projects, defining each project's needs, inputs, outputs, task type, and baseline. It checks that the data is complete and correctly shaped, then scores how well each project is framed. The selected example is a pavement repair prioritization project that uses factors such as age and traffic to predict a condition rating through regression. Its baseline is the last inspection rating, and it receives a perfect framing score of 5 out of 5. Data preparation. Data preparation in civil engineering turns raw information into a trustworthy foundation for machine learning. Engineers gather data from sources such as sensors, traffic counts, and inspection records. Then check that variables, units, measurement methods, and values are consistent and plausible. This step combines domain knowledge with computational practice to ensure the dataset accurately represents the real infrastructure problem. Data preparation ensures a dataset is clean, consistent, and ready for modeling. Missing values and outliers must be handled carefully because they may reflect either errors or meaningful real-world conditions. In civil engineering, this often includes aligning timestamps, converting units, merging records, and standardizing labels so mixed data sources do not create misleading patterns. After cleaning data, convert it into features and targets that match the machine learning task. Features are the inputs the model uses, and targets are the outcomes it predicts. Feature engineering can make raw data more useful, such as turning a construction date into pavement age. The dataset should also be prepared to avoid future data leaking into training, so evaluation remains fair and reliable. Python code, data preparation. Prepare civil engineering data for modeling by cleaning units, handling missing values, and making labels consistent. Then define features and targets carefully so the model uses accurate, well-structured inputs. We begin by importing NumPy and pandas, two core libraries for data preparation. NumPy supports efficient array handling and numerical operations, while pandas helps manage structured data using data frames. Together, they provide the basic tools needed to handle and transform data effectively. We create a small pandas data frame for bridge inspection data. Each bridge has a unique identifier, a span length in feet, and an age in years. One span value is missing, showing how the dataset can include incomplete information for later processing and analysis. The code builds a small bridge inspection dataset using pandas. It includes daily traffic volume to show bridge usage, deck ratings to describe condition with one missing value to handle later, and material names that need capitalization standardized for consistent processing. The code standardizes material labels by converting them all to lowercase. This keeps entries consistent, so differences in capitalization do not cause the same material to be treated as separate values during analysis or modeling. Each bridge span is converted from feet to meters by multiplying by the standard conversion factor, 0.3048. The converted values are stored in a new span meters column, keeping measurements consistent for accurate modeling and analysis. For the span and deck rating columns, missing values are replaced with each column's median. This keeps the data consistent while reducing the influence of outliers, since the median reflects the middle value rather than being pulled by extreme values. We create a traffic per meter feature by dividing daily traffic volume by the bridge span in meters. This shows how much traffic each meter of the bridge carries, helping relate traffic load to bridge size. Including this feature may improve the model's ability to make predictions. We prepare the model by choosing the input features and the target to predict. The features are bridge span, age, and traffic per meter, which are used to estimate the bridge deck condition. The target is the deck rating, giving the model a clear output for analysis. Before modeling, confirm that the feature data and target data have the same number of rows, so each input matches a target value. Also check that the features contain no missing values. These checks help ensure the data is clean, aligned, and ready for reliable model training. We first review the prepared dataset by checking how many rows it contains and which feature columns will be used as model inputs. The target is the deck rating, which is the value the model will predict. We also check the features for missing values, then preview the first prepared row with rounded values to confirm the data looks ready for modeling. This script prepares bridge inspection data for modeling by cleaning key fields, standardizing material names, converting span measurements to meters, and filling missing span and deck rating values with medians. It creates a traffic per meter feature, then uses span in meters, age, and traffic per meter as model inputs, with deck rating as the target. It also checks that the prepared features have no missing values and match the target length, then prints a brief summary of the prepared dataset. Train models. Training models in a machine learning pipeline means using prepared civil engineering data to help algorithms make predictions or classifications. This requires a clear problem, a defined target, and organized data for fair evaluation. The goal is to find useful patterns between inputs and outcomes, while choosing a model that fits the engineering question, the data, the acceptable error, and the practical impact of the prediction. Begin with simple models and baseline predictions before using more complex methods. A baseline, such as using past average productivity, shows whether a trained model with added factors like crew size or weather is actually improving performance enough to justify its complexity. In civil engineering, this comparison is especially important because models can affect safety, cost, and infrastructure decisions, so they should clearly outperform basic rules before being trusted. After selecting candidate models, train them on the training data and test them on separate data to see how well they generalize. This stage may involve adjusting features, comparing model types, and refining choices. The best model is not always the most accurate. It should also be understandable, stable, efficient, and useful for stakeholders. Good model selection combines technical evaluation with practical judgment about real-world decisions. Python code. Train models. After preparing the civil data, train simple models to establish a baseline. These baselines help show whether more advanced learning methods add value, while manual data splitting supports fair evaluation. We begin by importing NumPy to work efficiently with numerical data. It will help manage arrays for the concrete mixture components and their strengths, making later calculations and data handling easier. We set a fixed random seed with NumPy, so random operations give the same results each time the code runs. This makes experiments reproducible and helps with debugging. We create synthetic concrete mixture data by defining cement amounts from 280 to 420 and water amounts from 190 down to 155. These values represent different mixture compositions, and they are stored as floating point numbers for precise calculations. The concrete compressive strength values, measured in megapascals, are stored in a numerical array. This makes it easy to analyze and perform calculations on strength data from different concrete mixtures later in the script. The cement and water data are combined into one design matrix, where each row is a sample and each column is a feature. The strength values are copied into a separate target array. This keeps the input features and target values organized in the format needed for training and evaluating machine learning models. Before splitting the data, the code verifies that the inputs and targets contain the same number of samples. This confirms that every input has a matching output, which is necessary for reliable model training and evaluation. The data indices are first shuffled into a random order to help avoid bias when splitting the data set. Then, 75% of the samples are assigned to the training set, leaving the remaining data for testing. After shuffling the data indices, we use the first portion as the training set and the remaining portion as the testing set. This creates a random training subset while keeping separate data for evaluating the model. The data is split into training and testing sets by using separate indices. Features come from the design matrix, and target values come from the strength data, with matching indices used for each set. This manual split helps ensure the model is evaluated fairly and without bias. A baseline prediction uses the average training strength as the prediction for every test case. This creates a simple benchmark with the same size as the test data, helping show whether a model performs better than just predicting the training average. To prepare data for linear regression, add a column of ones to the training data to represent the intercept term. Combining this with the original features creates an augmented matrix, allowing the model to learn both the slope and the constant offset. We use NumPy's least squares method to fit a linear model to the training data. It finds the coefficients that minimize the squared differences between the actual and predicted values. These coefficients capture the relationship between the features and the target, and are then used to make predictions on new data. To predict test strengths, the test data is first augmented with an intercept column of ones. This augmented data is then multiplied by the trained model's coefficients, applying the linear regression model to produce the predicted values. We evaluate the model using mean absolute error, which shows the average size of the difference between predicted and actual values. First, we calculate this error for the baseline predictions to create a comparison point. Then, we calculate the same error for the trained linear model, allowing us to see whether the model improves on the baseline. The workflow summary reports the training and testing sample counts, then compares model performance using mean absolute error for both a baseline and a trained linear model. It also shows the linear model's rounded coefficients to indicate how the features relate to the target. The key takeaway is to check simple baselines before trusting more complex models. This script builds a simple linear regression model to predict concrete compressive strength from cement and water content. It creates reproducible synthetic data, splits it into training and test sets, and compares the model against a basic baseline that predicts the training average. After fitting the model with least squares, it reports test errors for both approaches along with the learned coefficients. The main lesson is to check a simple baseline before trusting a more complex model. Manual data splitting, random split. A random split divides a dataset by shuffling the observations and assigning some to training and the rest to testing. This helps the training data include varied patterns, while the test data checks how well the model performs on unseen cases. Keeping these sets separate is essential because testing on the same data used for training can give misleading accuracy and may not reflect real-world performance. When manually splitting data with Python and NumPy, shuffle whole rows so each example keeps its features and target value together. A common approach is to shuffle the row positions first, then use them to separate the data into training and test sets. This prevents labels from being mismatched and helps clarify what automated splitting tools do. Random splitting is appropriate when data points are independent and order does not matter, such as separate concrete strength measurements from different batches. It can be misleading for time-dependent data like traffic or rainfall, because future observations may leak into training and make results look too good. It can also overstate performance when similar records from the same project appear in both training and test sets. Choose random splitting only after considering how the data was collected and how the model will be used. Python code, random split. Manual random splitting helps keep related records aligned, while NumPy indices make the shuffling process clear and traceable. When working with civil datasets, evaluation must be handled carefully to ensure reliable results. We begin by importing NumPy, a library used to work efficiently with arrays and random shuffling. This prepares the script to manage and manipulate numerical data. We use NumPy's random module to create a random number generator and set its seed to 42. This makes the random sequence repeat the same way each time the code runs, which supports reproducible results. It is especially useful for consistent data shuffling, such as when splitting data into training and testing sets. Bridge features are stored in a two-dimensional NumPy array, where each row represents one bridge and each column represents a feature such as length, width, or height. This keeps each bridge's data organized and aligned with its target values, which is important for later analysis and machine learning tasks. The code stores bridge features in a NumPy array, with each row representing one bridge and each column holding measurements such as length, width, and height. These feature rows are matched to the corresponding condition ratings in the target data. Keeping this alignment is essential so the dataset remains accurate when it is later split into training and testing sets. A NumPy array is used to store the bridge condition ratings as the target values. Each rating lines up with the matching row of bridge features, so the data stays correctly paired. This alignment is important when preparing the data for tasks such as splitting it into training and test sets. First, check that the feature data and target values have the same number of entries, since each feature row must match one target value. An assertion enforces this alignment and catches mismatches early, helping prevent errors when the data is later split into training and test sets. We first count the data records in the features array so we know how many samples are available. Then we set aside 75% of the data for training and use the remaining 25% for testing. This gives the model enough data to learn while still leaving data to evaluate its performance. To choose the training set size, multiply the total number of rows by the training fraction. Then, check that the result is greater than 0 and less than the total row count, so the split includes both training and test data. To randomize a dataset, we first create a list of row positions from the first row to the last. A random generator then shuffles these positions, changing the order of the rows while keeping each row's values together. This helps create unbiased training and test sets without damaging the structure of the data. After shuffling the indices, we split them into two groups. The first portion becomes the training indices, and the remaining portion becomes the test indices. Because the split uses the shuffled order, both the training and test data are randomly sampled from the original dataset. Use the training indices to select the matching rows from both the features and the target data. This creates the training set while keeping each feature row paired with its correct target value. Maintaining this alignment is essential for accurate model training. To create the test data, select the feature rows and target values using the same test indices. This keeps each target correctly matched with its features and preserves the shuffled split. Keeping the test set separate allows the model to be evaluated fairly and without bias. We check that the training and test sets together contain the same number of records as the original data. This confirms the split did not lose or duplicate any rows and helps verify that the data partitioning was done correctly. This output gives a quick check of the prepared dataset. It reports the total number of records, how many are used for training, and how many are reserved for testing. It also shows the shuffled row order, then displays the first training row and its matching target to confirm that the data and labels are aligned correctly. This script shows how to randomly split a dataset with NumPy while keeping results reproducible. It checks that the bridge features and condition ratings have matching record counts, then uses a fixed random seed to shuffle the row indices. The shuffled data is divided into a 75% training set and a test set, preserving alignment between each feature row and its target. Finally, it confirms the record counts and prints a brief summary of the split and the first training example. Train test split. A train test split divides a dataset into one part for training a model and another for testing it. This helps estimate how well the model will perform on new data, rather than just on examples it has already seen. In civil engineering, this matters because models must predict future conditions, such as concrete strength or energy demand. If the same data is used for both training and testing, results can look too good because the model may simply memorize the data. To manually split data into training and testing sets with Python and NumPy, choose a training fraction, optionally shuffle the row order, and use the resulting indices to separate the data. Most rows should be used for training, with a smaller set kept for testing model performance. Always keep each row's features and target value aligned, because mismatches make the results invalid. Choose a train test split that matches the data structure and the engineering question. Random splitting is appropriate when observations are independent, but group data should not be mixed across training and testing because it can make accuracy look too high. For time-dependent data, train on earlier records and test on later ones. The goal is to estimate how well the model will perform on truly unseen information. Python code. Train, test, split. Manual splitting helps ensure honest model evaluation by keeping training and testing data clearly separated. In civil engineering datasets, each row must stay aligned with its correct target value. Using NumPy indices makes this splitting process transparent and easier to verify. We begin by importing NumPy, a Python library for efficient numerical work. Here, it supports basic array operations needed for a manual train test split, such as creating arrays, shuffling indices, and dividing the data. We create a NumPy random number generator with a seed of 42, so random results can be repeated. This makes operations like splitting data into training and testing sets consistent across different runs. The script stores measurements for 6 retaining walls in a 2-dimensional NumPy array. Each row represents one wall, and each column holds a measurement, such as height, thickness, or another dimension. This structure makes the data easier to analyze and manipulate later. This section adds several retaining wall observations to a NumPy array. Each observation records 3 features: wall height, thickness, and length, with values increasing across the entries. Storing the data in a NumPy array makes it easier to perform efficient numerical operations and manipulate the observations later in the script. The measured wall movement targets are stored in a NumPy array, with each value representing movement in millimeters for our retaining wall observation. This format supports efficient numerical work and keeps the target values aligned with their matching feature data. It also helps preserve the correct pairings when the data is later split into training and testing sets. First, we verify that the wall data and movement targets have the same number of entries. This check ensures every feature row has a matching target value, protecting data integrity before any further processing. We first count the rows in the wall data to find the total number of observations. Then we set aside 67% of the data for training, leaving the remaining portion for testing. This gives the model enough data to learn while still allowing its performance to be evaluated. Use the random generator's permutation method to shuffle row indices reproducibly, so the order stays the same each time the code runs with the fixed seed. Then determine the training set size by taking 67% of the total rows and rounding it to a whole number. After shuffling the data indices, we split them into training and testing groups. The first portion becomes the training set based on the chosen training size, and the remaining indices become the testing set. This creates separate data groups for building the model and evaluating its performance. The data is split into training and testing sets by using the chosen indices. Training indices select the matching feature rows from the wall data and target rows from the movement data, while testing indices do the same for evaluation data. This keeps features and targets aligned for both model training and testing. After splitting the data, we verify that the training and testing rows together match the original row count, so no data was lost. We also check that the feature rows and target values line up in both the training and testing sets. These checks help ensure the split preserved data integrity and kept each observation paired with its correct target. The output summarizes a manual train test split created with NumPy indices. It reports the total dataset size, the number of rows assigned to training and testing, and the selected indices for each group. It also shows the first target value from the training set as a quick example of the data used for training. This script shows how to create a reproducible train test split with NumPy for retaining wall data. It verifies that the feature rows match the movement targets, shuffles the row indices with a fixed random generator, and assigns about 2/3 of the data to training and the rest to testing. It then extracts the matching features and targets for each set and prints key details, such as the split sizes, selected indices, and a sample training target to confirm the split is correct. Train test split. A train test split separates data into one part for training a model and another for testing it. This gives a more realistic measure of how well the model can predict new cases, such as concrete strength or bridge conditions in civil engineering. If the same data is used for both learning and evaluation, the results can look too good because the model has already seen the answers. A clear split helps show why training and testing must stay separate. To manually split a dataset with Python and NumPy, create a reproducible split by working with row positions. Count the observations, shuffle their indices, then assign part of the shuffled indices to training and the rest to testing. Shuffling helps avoid bias from the original data order, so both sets better represent the full dataset. When splitting data for training and testing, match the split to the data structure and prediction goal. Random splits are fine when rows are independent, but civil engineering data often contains related records from the same bridge or project. Keeping related records together helps prevent data leakage and gives a more realistic test of how the model will perform on new situations. Python code, train test split. Manual splitting helps ensure honest model evaluation by making row separation reproducible and transparent. In civil datasets, using NumPy indices provides a clear way to control which rows are used for training and testing. We begin by importing NumPy, a library that helps manage arrays and perform numerical operations such as shuffling data efficiently. We create a small dataset of cement amounts for concrete samples measured in kilograms. The values are stored in a NumPy array where each number represents one sample's cement weight. This makes the data easy to analyze and combine with other related features later. We store each sample's water-to-cement ratio in an array because it is an important feature for the model. Keeping these ratios separate helps keep the dataset organized and makes it easier to combine them with other features later. We combine the cement weights and water cement ratios into one matrix by stacking them as side-by-side columns with NumPy's column stack function. This creates a single feature set, so both variables can be used together for later analysis or model training. The concrete strength targets are stored in a separate array measured in megapascals. Each value matches the corresponding row in the dataset, making it easier to manage the target data alongside the feature data, while keeping everything correctly aligned. Before splitting the data, check that the feature data and target values have the same number of rows. This ensures each set of features matches one target value and prevents misalignment during training and testing. We first count the observations by checking how many rows are in the feature data. Then we set aside 25% of the data for testing, leaving the rest for training and reserving a portion to evaluate model performance. To make row shuffling reproducible, initialize the random number generator with a fixed seed of 42. Then create a sequence of row indices from 0 up to the dataset size, which can be shuffled to reorder the data without changing the original dataset. The code first shuffles the row indices to randomize sample selection without changing the original data. It then sets the test set size by taking 25% of the total rows and rounding to the nearest whole number, creating a clear split between training and testing data. After shuffling the data indices, we split them into a test set and a training set. The test set gets the specified fraction of the data, while the remaining indices are used for training. This lets the model learn from most of the dataset and then be evaluated on data it has not seen before. Use the training indices to select the matching rows from the feature data and the corresponding strength values. This creates aligned training inputs and targets, ensuring the model learns from the correct pairs of data. Create the test set by using the chosen test indices to select the matching rows from both the feature data and the target values. This keeps the test inputs aligned with their correct outputs and separates them from the training data, so the model can be evaluated properly. To verify a train-test split, first confirm that the training and test rows together equal the original row count, so no data was lost. Then check that their indices do not overlap, ensuring each data point belongs to only one set and the split remains valid. The output gives a quick overview of the dataset split. It shows the total number of rows, how many are used for training and testing, and which original row indices belong to each set. It also displays the first training feature row and its matching target value in megapascals, providing a brief check of the training data structure. This script shows how to manually create a reproducible train-test split for a small concrete strength dataset using NumPy. It combines cement weight and water cement ratio as features, checks that they match the strength targets, then shuffles row indices with a fixed random seed. The shuffled data is split into training and testing sets with no overlap, and the script prints the split sizes and a few training examples. This gives a clear way to prepare civil engineering data for model evaluation. Baseline models, regression baselines. A regression baseline is a simple prediction method used as a benchmark for more advanced models. In civil engineering, it might predict concrete strength or traffic volume using a basic assumption, such as the average value from training data. Any complex model should perform better than this baseline. If it does not, it is not adding useful predictive value. A mean predictor is a simple regression baseline that uses the training set's average target value for every prediction. It is useful when targets are fairly symmetric, but the median can be better when outliers skew the average, such as with unusually expensive construction projects. Baselines can also use simple groups, like predicting averages by road class or building type. Good baselines should be simple, reproducible, and rely only on information available at prediction time. Regression baselines give a simple point of comparison for judging whether a model is truly useful. A complex model may still be valuable if it beats a basic prediction by a meaningful amount, even when its error seems large on its own. But if it only improves slightly over the baseline, its added complexity may not be justified, especially when it is hard to explain. Baselines also help reveal workflow problems and support responsible model development. Python code: regression baselines. Regression baselines use simple prediction rules to judge performance on continuous targets, which are common in civil engineering. They should be evaluated before moving on to more complex models. We import NumPy to work efficiently with numerical data using arrays, matrices, and mathematical operations. We also import Matplotlib's plotting tools to create visualizations that help interpret data and regression baseline results. We set a fixed seed for NumPy's random number generator, so random operations such as shuffling data produce the same results each time the code runs. Using the seed value 42 makes the process reproducible, which helps with debugging and comparing results across runs. We create two NumPy arrays for a simple concrete strength dataset. One stores the cement weight for each sample, and the other stores the matching compressive strength measurements. This paired data will be used to explore basic regression baselines. First, confirm that the cement measurements and strength measurements contain the same number of values. This ensures each cement value has a matching strength value, keeping the data consistent for analysis. The strength data indices are randomly shuffled using NumPy's random permutation method to avoid bias when splitting the data. Then, a split point is set at 75% of the dataset, so most of the data is used for training and the rest for testing. After shuffling the data indices, we split them into training and testing groups. The first 75% are used for training, and the remaining 25% are used for testing. This manual split gives control over the data distribution and supports a fair evaluation of model performance. We create the training and test target arrays by selecting the corresponding compressive strength values using their indices. These targets provide the actual values needed to compare baseline predictions with the test data. We create simple baseline predictions by finding the mean and median compressive strength in the training data. The mean gives the average training value, while the median gives the middle value and can be more robust when the data is skewed. These baselines provide a reference point for evaluating more complex models later. To create simple baseline predictions for the test set, we fill arrays with the training data's mean and median values. Each array matches the size of the test data and gives the same prediction for every test sample. These mean and median baselines provide a simple way to compare against the actual test values. The mean absolute error function uses NumPy to compare actual and predicted values. It finds the average absolute difference between them, showing how far predictions are from the true values on average. This gives a simple measure of prediction accuracy. We evaluate two simple baseline predictors by measuring their mean absolute error on the test data. One baseline predicts using the training data mean, and the other uses the training data median. Comparing these errors shows how well these basic strategies perform against the actual test values. This regression baseline example for concrete strength reports the training and test sample counts, then compares two simple predictors based on the training data, the mean strength and the median strength. It prints each baseline prediction, rounded for readability, and reports the mean absolute error for both approaches. These results provide a simple reference point for judging how well more advanced regression models perform. This plot compares actual concrete compressive strength test values with two simple regression baselines, mean predictions and median predictions. The specimen index is shown on the horizontal axis, and compressive strength in megapascals is shown on the vertical axis. A title, legend, and light grid make the chart easier to interpret before it is displayed for analysis. This script shows how to create simple regression baselines for predicting concrete strength. It splits the data into training and test sets, then uses the training targets to make two constant predictions, the average value and the median value. These predictions are evaluated on the test set using mean absolute error, and the results are printed. A plot then compares the actual test values with the two baseline predictions to show how well these simple methods perform. Regression baselines. A regression baseline is a simple prediction method used as a benchmark before building more complex models. In civil engineering, it may use typical values such as average strength, traffic volume, or settlement to set a basic standard. Any advanced model should perform better than this baseline. Otherwise, its added complexity is not justified. Baselines help confirm real learning and reduce the risk of misleading or unnecessarily complex models. Regression baselines use simple predictions from training data, such as the mean or median target value or a basic rule based on domain knowledge. The median is often better when extreme outliers could distort the average. Practical baselines, like recent measurements or historical averages, give a clear benchmark for judging whether a more complex model actually improves performance. Regression baselines should be tested on the same data as more advanced models so comparisons are fair and consistent. They give error metrics practical meaning by showing whether added model complexity is justified. A small improvement over a simple average prediction may not be useful, while a large improvement over a strong baseline suggests the input variables contain valuable predictive information. Python code, regression baselines. Regression baselines provide simple prediction rules for comparison. In civil engineering data, target values may include outliers, so evaluation should be handled carefully. Test data must remain held out to give an unbiased measure of performance. We begin by importing NumPy to handle numerical data efficiently with arrays, matrices, and mathematical operations. We also import Matplotlib's plotting tools so we can visualize the data and regression baseline results. To make random operations repeatable, we set a seed for NumPy's default random number generator using the value 42. This ensures the code produces the same random results each time, such as splitting the data consistently across runs. We create a small dataset with two arrays, bridge component ages in years, and their matching repair costs in thousands of dollars. The ages act as the independent variable, while the repair costs are the dependent variable for exploring regression baselines. One repair cost is a large outlier, which helps test how baseline predictions handle unusual civil engineering data. Make sure the ages and repair costs are each stored as one-dimensional data so they can be compared correctly. Then confirm that both sets contain the same number of values, because each age must match exactly one repair cost for the analysis to be valid. We first create a set of positions matching the repair cost data, then randomly shuffle those positions. This lets us split the data into training and test sets in a random order, reducing order-based bias and supporting a more reliable model. The data is split by using 75% of the indices for training. The training set takes the indices from the beginning up to that split point, while the test set uses the remaining indices after it. The repair cost data is split into separate training and testing targets using the chosen training and test indices. The training portion is used to build baseline models, while the testing portion is kept separate for evaluation. This ensures the model is assessed on data it has not seen before. We use the training data to create two simple baseline predictions for repair cost. The mean gives the average cost, while the median gives the middle cost after sorting the values. The median can be more reliable when the data includes outliers. We build two simple baseline predictions for the test cases. One that always predicts the training data's mean repair cost, and one that always predicts the training data's median repair cost. These constant predictions provide a basic comparison point for judging whether more complex models perform better. Mean absolute error measures prediction accuracy by finding the absolute difference between each actual value and its prediction. Then averaging those differences, the result shows the typical size of the prediction error, making it a common way to judge how closely predictions match real data. We evaluate the baseline models on the same test data by measuring mean absolute error. For both the mean baseline and the median baseline, we compare the actual test values with their predictions and average the absolute differences. This lets us see which baseline gives more accurate predictions. We first report how many cases are in the training and test sets to show the data split. Then we compare two simple baseline predictions for repair cost, the training average and the training median, both shown in thousands of dollars. Finally, we print the mean absolute error for each baseline on the test data, allowing us to see whether the mean or median gives more accurate predictions. The plot compares actual test repair costs with two simple baseline predictions. A scatter plot shows the real costs for the held-out test cases, while dashed and dotted horizontal lines show the training data mean and median. These baselines provide quick benchmarks for judging how well more advanced models match the actual costs. The plot is labeled to make the regression results easy to interpret. The x-axis identifies each held-out bridge component in the test set, while the y-axis shows repair cost in thousands of dollars. A clear title explains that the plot compares regression baselines for bridge repair cost, and the legend distinguishes the actual costs from the baseline predictions. The code adjusts the plot layout to prevent labels or elements from overlapping, then displays the plot. This lets us compare the actual test costs with the mean and median baseline predictions, helping assess how well those baselines estimate repair costs. This script tests simple regression baselines for predicting bridge repair costs. It splits the data into training and test sets, then uses the training costs to create mean and median predictions. These predictions are evaluated on the test set using mean absolute error, and the results show how well each basic baseline performs. A scatter plot compares the actual repair costs with the baseline predictions to make the comparison easier to understand. Regression baselines. A regression baseline is a simple prediction method used as a standard for judging more complex models. It might predict the average training value for tasks such as estimating concrete strength or traffic volume. If an advanced model cannot beat this baseline, it may not be learning useful patterns, or the data and features may be weak. Baselines help confirm that model improvements are real. Regression baselines help show whether a model is truly improving predictions, or only looks good because the target values are clustered. If many values are close to the average, a simple mean or median prediction may already perform reasonably well. A machine learning model should beat these simple or domain-based baselines by reducing error enough to justify its added complexity. A regression baseline gives teams a simple point of comparison for judging predictive models. It shows whether a model improves enough over a basic average prediction to justify added complexity. Baselines also support fair evaluation by separating training data used for development from test data used for validation. In practice, they help keep machine learning work honest, useful, and focused on real value. Python code, regression baselines. Regression baselines provide simple prediction rules for comparison. In civil engineering, many targets are continuous, so the training data must clearly define each baseline used. We import NumPy for efficient numerical calculations with arrays, and Matplotlib pyplot to create visualizations for plotting data and comparing predictions. We create a small concrete strength dataset using two aligned arrays. One stores cement content in kilograms per cubic meter, and the other stores the matching compressive strength values in megapascals. Together, these paired measurements provide the data needed for regression analysis. Before analysis, confirm that the cement and strength data have the same number of values, so each cement measurement matches a strength measurement. Also check that the strength data includes at least 4 values, which provides enough information for basic statistical analysis, such as setting baselines or splitting the data. The dataset is split manually into training and testing parts using fixed index groups. The first 6 data points are used for training, and the last 2 are reserved for testing. This creates a deterministic split, so the model can be evaluated on data it has not seen before. We separate the target strength values into training and testing sets using their corresponding indices. This gives the model the correct targets for learning and keeps a separate set for evaluating performance on unseen data. Mean and median regression baselines use simple summary values from the training targets as predictions. The mean gives the average target value, while the median gives a central value that is less affected by outliers. These baseline predictions provide a simple reference point for comparing performance on the test data. To create simple baseline predictions, use NumPy's full function to make arrays matching the test target shape. One array is filled with the mean prediction, and another with the median prediction. This gives every test case the same baseline value, which can later be used to compare model performance. To calculate mean absolute error with NumPy, compare the actual test values with each baseline prediction, using absolute differences. Averaging those differences gives the error for the mean baseline and for the median baseline. These values show how well each baseline predicts the test data. The output compares 2 simple baseline predictions for compressive strength, the training set mean and the training set median. It then reports the mean absolute error on the test set for each baseline, showing how far each simple prediction is from the actual test values on average. This provides a quick reference for judging whether later models improve on these basic approaches. The plot compares actual concrete compressive strength values with two simple regression baselines based on the mean and median predictions. Cement content is shown on the horizontal axis, and compressive strength is shown on the vertical axis. Different markers and line styles distinguish the real test data from the baseline predictions, while labels, a title, a legend, and a light grid make the chart easier to interpret. This visualization helps assess how well the mean and median baselines match the actual test results. This script tests simple regression baselines for predicting concrete strength from cement content. It splits the data into training and test sets, then uses the training mean and median as constant predictions for the test data. It compares these baselines using mean absolute error and prints the predictions and errors. A plot also contrasts the actual test values with the baseline estimates, showing how basic statistics can provide a simple reference point for regression performance. In this lecture, you learn to describe the steps in an end-to-end machine learning workflow for civil engineering data, implement a manual train-test split using simple Python and NumPy operations, and build baseline predictors for regression and classification before training complex models. In the next lecture, Lecture B, we will go over metrics and errors. Thank you for your attention. See you all in the next lecture.